Welcome to our deep dive into the fascinating world of satellite orbits. Today, we'll explore the different types of orbits that satellites use to circle our planet. It's not as simple as just launching something into space. We're talking about a delicate cosmic ballet. Each orbit serves a specific purpose. From low Earth orbit to geostationary orbit, we'll unravel the science behind these celestial paths. Get ready to expand your cosmic perspective. First up, we have the low Earth orbit, or LEO for short. This is the domain of speed demons, where satellites zip around our planet at an altitude of roughly 160 to 1,500 kilometers. Now imagine completing an orbit every 90 to 120 minutes. That's like circling the Earth 16 times a day. Why the rush? LEO's proximity to Earth makes it ideal for high resolution and rapid data transmission. Think Earth observation, remote sensing, even spying, but there's a trade-off. Satellites in LEO can only observe a small portion of Earth at any given time. It's like trying to study an ant colony through a straw. To get the full picture, you need a different perspective. That's where medium Earth orbit, or MEO, comes into play. Cruising at altitudes between 2,000 and 35,786 kilometers, MEO satellites have a wider field of view than their LEO counterparts. This sweet spot between LEO and GEO makes MEO ideal for navigation systems like GPS. You see, a constellation of MEO satellites can provide global coverage, allowing your smartphone to pinpoint your location with remarkable accuracy. And it's not just about finding your way. MEO satellites are also used for communication, especially in remote areas where terrestrial networks struggle to reach. Chapter 3. Now imagine a satellite perfectly synchronized with Earth's rotation, appearing stationary above a fixed point on the equator. That's the magic of geostationary orbit, or GEO. At an altitude of 35,786 kilometers, these satellites orbit at the same speed as Earth's spin, making them seem to hover motionless in the sky. This unique characteristic makes GEO the go-to orbit for telecommunications, broadcasting, and weather forecasting. Think about it, a single GEO satellite can cover nearly a third of the Earth's surface. That's like having a giant antenna in space, beaming down signals to millions of people. Chapter 4. To study Earth's changing environment in detail, you need a satellite with a consistent lighting angle. Enter the Sun-Synchronous Orbit, or SSO. SSO satellites orbit at 600 to 800 kilometers with a tilted orbital plane relative to the equator. This ensures they pass over the same spot at the same local solar time daily. Think of it like a well-timed sunbath. SSO satellites get consistent sunlight, allowing precise monitoring of Earth's surface. Chapter 5. Finally, let's talk about the Geostationary Transfer Orbit, or GTO. This elliptical orbit serves as a bridge between low Earth orbit and geostationary orbit. Imagine launching a satellite directly into GEO. It would require an enormous amount of energy, like trying to throw a baseball all the way to the moon. Instead, we use GTO as a cosmic stepping stone. A rocket launches the satellite into GTO, where it uses its own propulsion system to circularize its orbit and reach its final destination in GEO. It's a more efficient and cost-effective way to get to GEO, like taking a scenic route instead of a direct flight. Thanks for joining us on this journey through the different types of satellite orbits. From the rapid circuits of LEO to the stationary perch of GEO, we've seen how these celestial pathways enable us to connect, explore, and understand our planet in ways never before imagined. But our exploration of the cosmos doesn't end here. There's still so much more to discover, from the intricate dance of planets and moons to the mind-boggling vastness of the universe itself. So keep looking up, keep asking questions, and never stop exploring the wonders of the cosmos. Stay tuned for more fascinating insights into the world of space and technology.